So I'll start with this, this slide. This sort of sums up to me some of the pathways that we were hearing about earlier. We have an end user. An end user in this instance is an offshore engineer who's seeking to design a fairly complex structure. And over on the left here, we've got a scientist come engineer who's fascinated by the technology, fascinated by the science, but the ultimate requirement is for this guy to inform this guy in his decision making, and for this guy to communicate his requirements, and for both of them to really understand what's required, what can be done, what's fit for purpose. So I want to talk at that very practical level of all of this new technology effectively informing some of the decision-making requirements. And this is a schematic that shows the whole evolution of an offshore oil and gas project. So in the very early stages, offshore concession blocks are licensed by oil companies, and they then have to decide, make an economic decision as to whether they're going to start to evaluate whether there's a resource there. So that there are early decision points in financial resource allocation. They might start off by doing some seismic exploration, and if that looks good, start drilling. If the drilling results look favourable, then they might start to select a concept for developing that offshore oil field. And then we go through a whole series of design iterations through to the point of construction and installation and then operation. And my point with this diagram is that Metocean information is required at every step along this route. In these very early stages, very little money is available, and it's not until full sanction of the scheme development that more significant sums of money become available. So I'm going to look at three applications here. The first one is a conventional fixed jacket offshore structure. So this can be a steel or a concrete substructure on the continental shelf at water depths of a few tens of meters, limiting depth perhaps just about 100 meters. So we've got the jacket, we've got the topsides, the derrick, the helideck, etc. And we're concerned with designing the platform to operate safely over its design lifetime, which may be of the order of 40 years. Now, there are many design requirements here. One of the interesting ones is setting the deck elevation of the lowest deck on the structure. You can see in this photograph we've got a large breaking wave where we've got water starting to impact on the cellar deck of the structure. Now, a key constraint is to avoid getting green water, that's sort of coherent water, not the very aerated breaking water, avoiding green water slamming on that lower deck. So we've got to determine the extreme combination of water level and wave crest height. Many other design requirements there too. A second application is looking at a floating structure. Now, I said that the steel jacket is probably good to about 100 meters water depth. Offshore Brazil and West Africa, we're now producing oil in water depths in excess of 3,000 meters. And you can't physically build a steel jacket to work in those depths. So we tend to use some sort of floating production system. And here we have, it's called an FPSO, a floating production storage and offloading facility. It's essentially a big ship with containment, and it has what's called a turret mooring to a complex array of anchors. And then from the wellheads on the seabed, the oil flows up through flow lines through quite a complex arrangement here, and we've then got oil containment in the FPSO. Shuttle tankers take the oil off the FPSO and take it to market. So, in contrast to the fixed structure, we've got a much more dynamic structure here, or a set of coupled structures. So we need much more information about the physical environment. We're concerned not only with the wave height and the water level, we're concerned with the current and the wind, and we're concerned about the combination of those factors, how the assembly aligns to the joint influences of current and wind, what the relative motions of the shuttle tanker and the FPSO are, the loadings on all of the subsea infrastructure. And the third application is looking at installation. So here, we've got the concrete sub-base for a jacket structure. And here we've got the topsides that are floating on an installation barge. And the game is to land that topsides safely on the barge, on the base. So we've got a locating pin here, and we've got a receptacle here on one of the piles, and all we have to do is float the barge down the middle of those piles and deballast it and drop it down. And you might think that's straightforward. That's it at the end of the operation. Now, that is an unbelievably complex and risky operation that requires a safe working envelope of limiting cross currents, limiting winds, limiting sea state, and particularly limiting swell, because unless we've got all of those things in alignment, then it's going to be a really hazardous operation.
How many hours? How many hours do you
I think the actual operation from somebody deciding go is about 18 hours for that. But it goes back months and years in the planning. You've got to get all of that spread out to the field in the first instance. Here, this is offshore in the Philippines, where you've got to mobilise things from Korea, from other parts of the world, and get it all there, and then you've got to find the working window to get it in. So you need really good information in the planning phases of that, as well as the end execution. So I like this continuum of data, information, knowledge, and wisdom. I think a lot of what we talk about in remote sensing is about getting data. A lot of what I do is turning that data into information and using our collective knowledge to inform engineering decision making. The spatial context, I think with much remote sensing, we have to start by thinking globally. For a particular oil field development, we're concerned with a very defined geography, and not only that, we're concerned with a given point on a structure. If we want to know how much steel to put into that helideck to make it safe, then we've got to come up with an objective number to inform the engineering design. So we have to go from the global to the regional to the local to the very localized in determining numbers to throw over that brick wall for the design engineer to use. And that's often taking things a lot further than the raw data or the calibrated data that comes out of a satellite sensor. What you see on the left here is an extreme value extrapolation. So what we often use in engineering design is a 100-year extreme value. That would be the value that statistically would be equaled or exceeded once in a period of 100 years. So in this instance, we're extrapolating significant wave height, and so we're taking a limited population of data. We're fitting some sort of probability distribution function to it, and then we're extending beyond the scope of those observations out to our best estimate of the 100-year extreme. And in the right-hand diagram, those are contours of extreme combinations, in this case of significant wave height and spectral peak wave period, but that could be wave height and current, wave height and wind speed, dependent on the application. And then in operations planning, we're concerned with quite a number of statistical representations of past conditions and using those to infer what's most likely to happen during the period that we're planning for. With something like the Topside Floatover that I talked about earlier, we want to get a very reliable quantification of the likelihood of being able to undertake that operation safely, and we might want to work out how long we're likely to have to wait for a safe window to undertake that operation. The sort of spread I showed there is going to cost hundreds of thousands, maybe millions of dollars a day to have sitting on standby. So you can very quickly rack up huge amounts of cost. And this is just a representation of analysis of a long-term data set to come up with some of those waiting time statistics. So the sort of parameters that I work with, wind speed is a key parameter, wave height, period, direction, spectral shape, current speed and direction and profile, water level. Now, some of those parameters we can get at from remote sensing readily. We can get at wind speed from Scatterometer, wave height from Altimeter, current speed and direction we can infer something about geostrophic velocity from sea level anomaly from altimetry, and we can get water level from altimetry. But we're quite limited in getting the sort of information that we need to inform our design. So ideally, we want reliable long-term time history data at a specific point in the ocean. And we want it for all of those parameters. And that's really how the oil industry works with these things. Now, what I want to point out is you can't readily produce that sort of information from satellite remote sensing, but there's a lot that you can use from satellite remote sensing to inform these long-term data sets. As well as this objective time series data for analysis, it sort of comes in the wisdom box, I suppose. You need an appreciation of the dominant physical processes that are occurring in a given region. It might be the monsoon, it might be the timing of the onset and cessation of the monsoon that's important. It might be the occurrence of tropical cyclones. There might be anomalous katabatic wind systems. There's a whole raft of different anomalies. And some of those aren't readily represented in the remote sensing data stream. So those are ones we have to watch out for. And then we've got the temporal context. So I've put here routine operational planning. That might be sending a supply boat out to an offshore facility. That's something that happens, if not daily, then a few times a week. So we're looking there at information over the coming days. Special operations planning, well, that Floatover was an example where we want to be planning months, if not a few years in advance to get that operation right. And then in structural design, we're designing the sort of facilities I showed you earlier, and we're concerned to design a facility for an operational lifetime of maybe 40 or 50 years. So we need estimates of the likely worst case conditions over that lifespan of the operating structure. If we look now at data sources, perhaps the longest term data source is visual observations from mariners, from ships. And we've got systematic ships records going back over 150 years. But you know, these are visual observations, they're reasonably subjective, and you know, their reliability is limited. Water level records, we've got relatively good long-term water level records at a limited number of stations. So at Newlyn we've got data going back well over 100 years now. Meteorological station records, at many locations we've got tens of years of records. The offshore oil industries recognise the importance of in-situ monitoring, and many of the key platforms have quite advanced data collection systems. So we've got tens of years of such data. And then we've got satellite measurements. And I guess now we've accumulated a few tens of years of data. Altimetry is an area that I work with, and really we've got data going back to the early 90s. So we've got sort of continuous data since then from a variable number of satellites, different sensors, but we're starting to construct now an objective, reasonably long-term record of global altimetry. And I'm going to come on to talk about numerical modelling and how that can tie all of these things together. The other thing we do is to deploy instruments in the ocean. What you see here on the left is a floating wave buoy. In the middle is a downward-looking wave radar, and the right is an upward-looking acoustic wave gauge. Now, in most cases where there's an oil field to be developed, there would be a deployment of in-situ instrumentation. There's a long lead time for doing this. If it's in a remote area, it can be extremely expensive, and realistically, we're probably only going to get a few months, maybe a couple of years of data if we're lucky. So again, thinking back to that data extrapolation out to the 100-year extreme, we need a longer population than 1 or 2 years to get reliable long-term statistics. So that's really where remote sensing comes into things. The radar altimeter, we can infer from the roughness of the return signal, we can infer significant wave height as a parameter. The footprint or the cone of a conventional radar altimeter is perhaps around 7 kilometers, so it's not a pinpoint. There are limitations in coastal waters, but we've got this global swathe of data that is of great use in our work. We saw earlier about the orbital trajectory from a polar orbiter. So with altimetry satellites, we're getting typically one cycle per day. So it's taking quite a number of days to construct a full global lattice of observation. So we're certainly not getting that single point continuous high frequency time series that and we've got the issues of orbit. There's a trade-off between repeat sampling rate and spatial resolution. So the finer the spatial resolution, the longer the repeat pass at a given point. So in our line of work, we use numerical modelling as a way of best harnessing the information that's available from remote sensing and in-situ measurement. So again, we start with global or regional scale models, and this is our global wave model. And this is a bit of a busy diagram, but we start with long-term wind model data, and we can calibrate that wind data using scatterometer observations, and we can validate the scatterometer observations by long-term in-situ buoy measurements. And then we have a calibrated global wind history, and we can then use that to force a global wave model, and then we can further calibrate, validate the output from that wave model using independent radar altimeter observations. So we've got this sort of cycle of using in situ measurements, scatterometry and altimetry to enhance the quality of the model data that we start with. So this is just a daily coverage of swath scatterometry, and that's the repeat coverage over 1 month from Altimetry in the Gulf of Mexico. Now, our model systems have a certain grid resolution, and this is an example. This is one grid point in our model, this blue square, and typically in our scheme of things we would define a radius of influence around that grid point, and we collect all of the historical altimeter passes within that radius of influence, and then we subset our continuous numerical model hindcast so that we form a time series of concurrent pairs of model, simulation and satellite observation. And then we can do some comparison between the raw model output and the satellite observation. In the left-hand diagram, we're just using a simple linear regression to look for any systematic bias and scatter in the data. And in the right-hand diagram, we're overlaying the probability of exceedance distributions of the model hindcast in blue, and the in this case it's a buoy based set of measurements. So if we believe the buoy data, then we can apply a correction to the model data so that the exceedance distributions of those concurrent data overlie each other, and then we can apply that to the longer term time history. So different forms of data complementing each other, and it's quite often the case that we see the model diverges from observation in more energetic sea states. I'm going to skip through these because I'm conscious of. So we have a global model system and then a series of nested regional model systems. And we use this combination of buoy data, model and remote sensing for calibration in the work that we do. I'll quickly show you the second example. This is work we've been doing with the Met Office and an American company, Ocean Weather, where we've developed an ocean circulation model for West Africa. So we've got a layered ocean circulation model at 1/36th degree resolution with 75 layers in the vertical. And we've run this model for a 20-year duration. So the idea is we have a competent long-term set of time history data to use for engineering, design and operations planning. And with this model we're using assimilation rather than point-specific calibration. So on a daily basis we're assimilating surface temperature, surface height, we're assimilating ocean density profile data from Argo floats and sea ice concentration from satellite. We've also used altimeter data for constructing a global tidal model. So this can give us tidal elevation and depth average tidal current. And just a couple of slides to finish off, showing how if we've got these global long-term time histories, we can look both at an individual point and we can construct spatial statistics. So here we're looking at the 10% quantile significant wave height in the Indian Ocean for a particular month. So that would be very useful, so for planning a ship passage that's sensitive to a given threshold in sea state. And this is looking at wave severity off the east coast of Africa, looking at the wave period distribution at various points going up through the Mozambique Channel up to Somalia. So I could speak for hours on this, but I hope that's given you a sort of bit of a flavour for what we do. I suppose if you like, they're fairly dirty, pragmatic applications of remote sense data. I think that the remote sense data is helping significantly to inform what we do, but it doesn't work standalone in our applications. It only works by this broad combination.
So we'll take one or two questions if anybody's got questions. Tim?
Do you take into account projected sea level rise as a result of climate change into the 40-year planning horizons for the sort of offshore installations, etc.? If so, how do you do it and what data do you use?
Okay, so we use a sort of best estimate based on the current trend. And sort of a extrapolation of what we're seeing at the moment. And I think that's accepted perhaps as the pragmatic thing to do at the moment. What we're less good at doing is making any assessment of the likely variability in wave height or wind speed severity over that design horizon. So that remains a big question. We're more using a statistical analysis of the constellations to extrapolate into the future.
Is it true that the things you talk about in terms of using radar and such on the wind speed or wind direction work quite well in open oceans, but not so well in coastal areas?
Yes, it's a very good point. So certainly with conventional radar altimetry, we've had this landmask effect where within a few tens of kilometres of the coast, we're just not getting reliable altimetry. And that means that we have to calibrate our models tens of kilometres offshore and then use a numerical wave transformation to bring the offshore wave climate in. There's a lot of work going on now in swath altimetry and reprocessing of altimeter data to estimate conditions closer inshore. And I think there'll be a lot of benefit coming out of that in due course as far as everything's concerned.
What data would you want the ARGOSS at the moment from satellite?
Okay. One example, I'm probably thinking quite a few. The Congo River, where it flows out into the Atlantic, there's a very strong low salinity jet with the plume of the river outflow. Now, there's a lot of oil fields in northern Angola that are impacted by that plume. And if you've got a cloud-free day, you can see it beautifully with a visible image. but when you do systematic analysis, you find for 85% of the time you've got cloud cover. So that's one example, delineation of that pool. Sensors that are cloud penetrating of sufficiently high resolution to see where that plume is at any moment in time.
Enough resolution.
Well, with the work we've done, we've not been able to get high enough resolution to the operationally beneficial. Another example, using altimetry to assimilate emotion circulation models works well in general terms, but often where there's an ocean front, we see that's where very strong flows occur. And because of the footprint of the altimeter, we're not able to detect accurately enough the steep gradient of the front where it really matters. So again, if we could get finer spatial resolution there, that would help enormously. I'm sure there's many other instances.
Thank you very much. Thank you.